Now we'll discuss the chain rule. And before, when we just had a function of x, then we could say that dy dt was dy dx times dx dt, where x was a function of t. Well, suppose z is a function of t. So we have f of x of t and y of t. Then we would say that dz dt is the partial of f with respect to x times dx dt plus the partial of f with respect to y times dy dt. Now you have to do the partials of f because f is a function of two variables and x and y are just a function of one variable. Now z has to be differentiable function of x and y, and x and y are differentiable functions of t. So when we talk about implicit differentiation, we start with an equation equal to 0 in two variables. And let me just state the implicit function theorem. First, you have to have a couple of conditions. The first one is f is defined on an open circle containing the point AB. F of AB is equal to 0, and Fy of AB is not equal to 0. The partial of f with respect to y at the point is not 0. And f of x and f of y are continuous on the above disk, on that open circle. Okay, if all those are true, then we can say that f of xy equals 0 defines y as a function of x near AB, and the derivative of f is dy dx is equal to the partial of f with respect to x divided by the partial of f with respect to y, and that's minus the partial of f over the partial of, I don't need that symbol. Let me just write it like this with these symbols, f with respect to x, f with respect to y. Now I'm going to prove this because it's very easy to prove. Okay. Oh, I'm messing up. All right. Now, let's do the proof. If z is equal to f of xy, little f, and f of x, y, z then is equal to f of x, y, function of x, z is a function of x and y. That equals 0. And f and little f are differentiable. Now we can say that the partial of f with respect to x times the partial of x with respect to x plus f with respect to y, y with respect to x, f with respect to z, z with respect to x, that's all equal to 0. Now that's just 1, and y with respect to x is 0. Y doesn't depend on x. So now we have the partial of f with respect to x is equal to the negative f with respect to z times dz dx. And if df dz is not 0, then the partial of z with respect to x is negative fx over fz, and partial of z with respect to y, we can do the same thing, is negative fy over fz. Now that's not the proof, that's just extending it to 3 variables, where z is a function of x and y. Okay, so you can look at the homework problems, example ones that I do for you, to see how some of these are done.